Good afternoon. Am I audible?
Yes, sir.
Okay. So, how did you perform that experiment?
It was curious, sir.
Okay. So, you did it in plastic bottle.
Yeah, in a plastic bottle.
Okay, great. Okay, so I will start now. Because it's 4:10. So, were there any more students like who started this course, like who joined along? I think they were not some any student with you, your batch, right? In your college who took this course.
No, sir. No one from my college.
Okay. Okay. Yeah, because in the starting class the strength was nice, but it is now completely reduced. It's okay. I think in the other class also the strength is not much. Other class. So I think
Other class, I have not attended the other class.
okay, great. Oh, okay. Yeah.
Sir, can you tell a bit more about cloud condensation nuclei?
Okay. A bit more about cloud condensation nuclei. What I will do is that in detail I will cover in next class. But one thing which you should understand is that what is the importance of this cloud condensation nuclei. So as the name suggests, that when we have condensation in the atmosphere and when we have the formation of cloud, you need a certain surface. See, any surface, any condensation process which we have, it requires some surface to occur. For example, I gave the example of when you take out cold water bottle out from your fridge and you keep it on table. Then after some time, you see that droplets start forming on the outer surface of the bottle. That water, it's just condensation because it is very cold, and then suddenly it's warm and moist air which is in the warm and moist air which is surrounding this bottle. The the air which is very close to this cold surface, their temperature reduces such that it reaches a dew point, and at dew point it becomes saturated. The air which is very close to the surface of the bottle gets saturated, and it starts forming water. Condensation starts, and the vapor which is surrounding the bottle, they convert into water, and that what you see. If there was no surface, then you could have not seen those water. Okay, because always condensation requires some surface on which it occurs. So similarly, cloud cannot form. Cloud requires three things, as I told yesterday, that it requires moisture. That is, your air parcel must have some moisture in it. Then this air parcel should be cooled down to a dew point temperature. That is a temperature at which it becomes completely saturated, and after that, it condensation starts. And the third thing is you need a surface around which condensation can take place, around which condensation take place. So in our atmosphere, so in our atmosphere, there are a number of very small particles, as in the order of we did in the last class. Maybe yeah. So the typical radius or size of this condensation nuclei is in the order of 2 into almost 2 into 10 to the power minus 8 meter, or you can say it's 0.002 microns or micrometers. So these are very small spherical particles which are there in our atmosphere, or some people also call them as some kind of aerosols. And these are the surface around which the water vapor condenses to form cloud. So this is the very basic thing of cloud condensation nuclei, and these are very necessary for the condensation of the for the process of cloud formations. So so for example, the detail of it, like the concentration or the distribution of this cloud condensation nuclei CCN also depends upon places. Like in some places, they are present in large abundance. In some places, they are not that abundant. So depending upon that, also your cloud formation is dependent on that also, the presence of this cloud condensation nuclei. So in short, I can say that. And detail of it, what a different kind of CCN and all those things, maybe I will do in the next class. So you can just take away is that in order to form a cloud, you need some surface, and the CCN provide the surface on which the condensation take place. Is it clear?
Yes, sir.
Okay, so now we'll start with the class. So last class we learned about three kind of lapse rate. I would just revise it again. I think one confusion was there regarding naming. So first is the dry adiabatic lapse rate, or which is abbreviated as DALR. So it is given by this symbol or maybe this symbol gamma D. It is minus 9.8 Kelvin per kilometer. So this is called dry adiabatic lapse rate. The second kind of lapse rate is, suppose this means that your air parcel, in this case it means air parcel does not have any moisture. By any moisture I mean mixing ratio is zero. That is 0 gram of water vapor in 1 kilogram of dry air. So that is a very idealistic case. It is only possible in some desert area where there is no water vapor at all. But the more realistic case is the moist adiabatic lapse rate. Okay, which is abbreviated as MALR. This is for the case when air parcel has water vapor in it or moisture in it, but that parcel is not saturated. Parcel is not saturated. So in that case, in this kind of parcel which has moisture in it, but the parcel is not saturated, they will follow this moist adiabatic lapse rate, whose value is given by this, or maybe gamma m also, is equal to I think gamma d times 1 minus 0.9 W, which we did yesterday, Kelvin per kilometer. Okay, so as you can say that W is always positive or greater than 0. It can be 0 greater than 0. So this value is always, gamma m is always less than slightly, or at least slightly less than gamma d. Okay, or maybe equal to also. If W is 0, then gamma m is equal to gamma d. Okay, now the third case is saturated adiabatic lapse rate, which is SALR. This is for the air parcel which has moisture, and also the parcel is saturated. Parcel is saturated. That is, its relative humidity is 100%. In that case, parcel will follow this moist saturated adiabatic lapse rate, which whose value we derived yesterday. I will write his W, gamma W. It came out to be so minus G by Cp 1 plus this quantity minus G by Cp, which is nothing but dry adiabatic lapse rate times 1 plus LV upon G dWs by dZ. So this is the lapse rate for a parcel which is saturated, and also it is saturated, and obviously it has moisture in it. That's why it is saturated. So these are basically three kind of adiabatic lapse rate which we have in atmosphere, and as you can see that gamma D is always greater than gamma D is always greater than gamma M is always greater than gamma W. So this is a very important point. Okay, is this clear? This three kind of adiabatic lapse rate.
Yes, sir.
Okay, so now what we'll do is that yesterday we did some calculation that suppose there is some air parcel at some surface, and this is the temperature profile of the atmosphere, which is around some 6 Kelvin per kilometer, and some air parcel is there which has moisture in it but is unsaturated. Since it has moisture in it and it is unsaturated, it will follow this. Mostly gamma M and gamma D are always very close to each other, because this W value is such that mostly this are very very close to each other. So this initially parcel will follow this gamma M or gamma D, whatever you can say, up to a point which is called LCL, lifting condensation level. At this point, the saturation start take place. That is, the air parcel is saturated, and after that it will follow gamma W. It's because now it is saturated, so after that it will follow this gamma W lapse rate. So at this point, cloud starts forming, because after this water is already the parcel is already saturated. If you further lift the parcel, further cool down, so further cooling down will create condensation and clouds. So LCL is the base of cloud. So it is just an extra thing. It's not there in your online lecture. So I will just help you in deriving. Suppose if someone asks you to estimate the height of the base of cloud. By height of cloud, I mean the base of the cloud, height of the cloud from surface. How can you estimate the height of the cloud from surface if you just know its surface information, like the surface temperature and the surface dew point temperature? So is there a way we can derive equation through which we can calculate the height of the cloud from the surface? Yes, there is a way to do that. So in order to do that, first of all, what we'll do is that I will first write the very famous equation in thermodynamics, which is called Clausius Clapeyron equation. You can see the derivations from that book, Rogers and Young. So I'm just writing the equation. So the Clausius Clapeyron equation is dEs by dt is equal to minus LVES upon RVT square. So it just relates the change in the saturation vapor pressure with the change in the temperature. So the ratio of these two things, dEs by dt, is given by this LVS by RVT square, where your LV is your latent heat of vaporization. Okay, ES is your saturation vapor pressure, RV is your specific constant of water vapor, and T is the temperature. So this is a very famous equation. Through it establishes the relation between the saturation vapor pressure and temperature. Okay. So suppose there is an air parcel which reaches this LCL point. So after reaching this LCL point, it will start condensation will start occur. So at this point at LCL, we know that the temperature of the parcel will become equal to the dew point temperature at that level, because then only condensation will occur. We know that dew point temperature is the temperature to which an air parcel must be cooled so that it becomes saturated. So at LCL, the temperature of the parcel must be equal to TD. And also at LCLs, your vapor pressure of the air is equal to the saturation vapor pressure, because F is equal to 1, and F is what? F is W upon WS, or we can also write upon E upon ES. So since F is equal to 1, so the amount of vapor which is present in the parcel is equal to the saturation vapor pressure at that temperature. So we'll just use 2 in 1 to get 3. You will use 2 in 1. So what we can write is that dE by dt, we are replacing ES with E and T with TD, is equal to minus LVE upon RV TD square. Okay, so just we have replaced these quantities. So let us name this as equation 3. Okay. Now what we'll do is that we know that the parcel is undergoing adiabatic process, following the adiabatic curve, or you can say it following or undergoing as the parcel is rising, it is going adiabatic expansion, because we are assuming that parcel is not exchanging heat from the environment. And so for adiabatic process, we have this, you must have learned in the thermodynamic course. Poisson equation is there. Tp minus Tp to the power minus chi is constant. So, where T is the temperature, P is the pressure, and chi is the ratio of R upon Cp. So you take log both sides, so you'll get chi log P. Now P is pressure. Here we are talking about the vapor pressure. So we can just replace P with E. So what, and just differentiate this equation. So we'll get, if we differentiate this equation, we'll get what? 1 upon T dt. Chi is a constant, so it will come out of differentiation. dE by E. So we just replace P by E. Okay. Therefore, we can write dE by E is equal to 1 upon chi dt by t. This is equation 4. Okay. So what I will do is that now from 4 and 3, we can write 3 at like this also. dE upon E is equal to minus LV dTd upon. Okay, so we can write this also. So we just equation, this is equation 3. So from 3 and 4, we just replace dE by E as 1 by chi dt by t. So it will become or your dTd is equal to minus of RV upon chi Td square upon LV T C and then dt. Okay, so this is your equation. So what is the importance of the equation is that we will understand it later when in the next part. So this just relates your change in the dew point temperature with the change in the temperature. So what is it? So what is DT and DTD and DT? What changes are you talking about? Suppose you are at some surface, you are at surface, and the cloud is situated at some height. This is a cloud. Okay, at surface where height is zero. So let us say the temperature at the surface is T, and also at the surface the dew point temperature is TD1. Similarly, at the base of height, at the base of cloud, this is your LCL, lifting condensation level, where the cloud starts forming. At this, suppose the temperature will be equal to the dew point temperature will be equal to TD2, and the temperature, ambient temperature will be equal to the condensation temperature. Why condensation? Because at this temperature, at this level, clouds start forming. So obviously the temperature of the parcel will be equal to the condensation temperature. So, and this is the height which we want to estimate, delta Z. Suppose this is some Z value. So delta Z we want to calculate, which is basically Z only because this is base we have taken to be 0. So two things we can write from here. Delta T, which this equation which you're talking, delta T, this is basically difference in the temperature Tc minus T. Okay, this is T minus Tc. Now another thing which we can write is that this T minus Tc will be what? If we just take, because up to this point the parcel will follow the dry adiabatic lapse rate or moist adiabatic lapse rate, which is roughly equal to 10 Kelvin per kilometer. So we know that at this point, if the lapse rate is 10 Kelvin per kilometer and delta Z is the height, so the change in temperature will be lapse rate times delta Z. Or I can just write it as 10 times delta Z. Is this clear at this point? I will go slowly so that you understand. So this is basically the difference in the temperature between surface and the base of the cloud. Since up to this point, the parcel will follow the parcel which is being risen from this point to this point. So that will follow the adiabatic lapse rate. So the temperature will form at the rate of 10 Kelvin per kilometer. So at Z kilometer, for Z distance, it will be, change in temperature will be 10 times delta Z. Per kilometer 10 Kelvin fall is there. So for delta Z distance, it will be 10 into delta Z. Okay, this is equation 6. Similarly, you can write the change the dew point at two places. So it will be TD1 minus TD2. Now, now you know this TD1 will remain TD1 only, but this dew point temperature at the base of the cloud will be equal to what? It will be equal to Tc because both temperature are equal, because dew point and condensation temperature are equal. It is a temperature at which the convection starts taking place. So it will be equal to Tc. This is delta Td. Okay, so we have delta T, we have delta Td. So now what we'll do is that from equation 3, this equation, or from equation 5, this equation, we know that this, for general case, like for Td is equal to, say, if we take some, for normal case, then this value is in general order of 1 by 6 of delta T. This is a relation between delta Td and delta T. This is an approximate relation for general value. So delta Td is 1 by 6 delta T. So similarly, we can write this as delta Td is 1 by 6 of delta T where delta t is what? 10 times delta z. Okay. Now what we'll do is that we'll take a 7 minus 6. This derivation is not that important. End result will be important. So derivation you can just go through once and twice and you will able to do. When you do 7 minus 6, it is delta td minus delta t. What you will get is delta td minus delta t. It is 1 by 6 minus delta t is what? 10 delta z. And delta td is what? It is td1 minus tc. And delta t is t minus tc. This will become minus 50 delta z by 6. This will cancel out. So finally, your delta z will be 6 upon 50. I'm switching the sign. So t minus td1. Okay, so this is the height of the cloud from surface. This is equal to 0.12 t minus td1. So this is the height of the cloud. So derivation you can practice later, but what I will do is that, so just based where what is this t? T is the surface temperature and TD1 is the dew point temperature at surface. So just by just knowing the surface temperature and dew point temperature at surface, you can estimate at what height the cloud will form. So for let us take one example. Let's take an example. Suppose at the surface your temperature is 277 Kelvin and the dew point temperature at surface is suppose 273. So obviously, since temperature is greater than dew point temperature, no cloud is formed at surface. First thing you can say is that no cloud formed at surface. So the parcel will be taken to some height for the formation of cloud. Only at some height, only the cloud will form. At the surface, the temperature is greater than the dew point temperature, so no cloud is formed. So at what height the cloud will form? So you can just calculate it by delta z is equal to 0.12 t minus td, the dew point at the surface. So it will come out to be 0.48 kilometers. So this is in kilometers. So you can say that at the height of 480 meters, given this condition that the surface temperature is 277 kilometer and the dew point temperature, if you know, you can calculate that at what height the LCL will lie. This is delta Z is what actually LCL, lifting condensation level. So in this way, you can estimate the height of cloud if you have the information about the temperature, the surface, and also the dew point temperature at the surface. Or suppose if you take more realistic example, suppose in our place where temperature is suppose in some 30 degrees centigrade, so it is 293 Kelvin, and dew point temperature maybe you can take at 18 degrees centigrade, so it will be no, sorry, this is I've taken 30, so it will be 303. This is suppose in typical summer in our India, suppose the temperature is 303 Kelvin and the dew point is 18 degrees centigrade, which is 291. So you can just calculate at what height the cloud will start forming or the LCL will be there. It will be 0.12 times 9 into 12. Sorry, yeah, 9 through 12. So it will be what? 12 times 1440. Okay, so at 1.44 kilometers, will be 1.44 kilometers. So at around 1.5 kilometer height, the cloud will form. So the base of cloud, or LCL, lies will lie at this altitude. It is a very simple and important formula. You can just remember this. Maybe they will not ask question in the paper, but you can remember it for future. So this is a typical height of the cloud, or LCL, in our Indian place, if we can consider. In hilly region, the temperature is very temperature is small. Temperature is not that high. In that case, the height of cloud is also less. So that is also observed. When you go to the hilly region, the cloud are very close. They are not very high. So that is another reason. Okay. So is it clear? Derivation you can just go through once again, and you will be able to do that. Okay. So I will just go ahead. Another thing which is important is that fog. Have you heard this? You must have heard this name a lot, especially in the winter season in North India. When we have a lot of temperature difference, like when the night is very cold, in the morning we get a lot of fog. Okay. So what is fog? In simple terms, they are just clouds only. It is actually clouds. It is actually cloud forming near the near or at the surface. So the fog is nothing. It's also a kind of cloud only, which forms near or at the surface of Earth. This is a basic definition of fog. So some of the facts: it forms when air saturates. So this is very simple thing. Simple means very obvious thing, that air must be saturated. That is, relative humidity must be equal to 100%. Then only this will form. Fog will form. The second is, once the saturation occurs, the water vapor which is there in the air, it must condense on small particles, or CN, which we understand. Small particles, CCN, cloud condensation nuclei, to form liquid droplets. Liquid droplets, or in other words, we can call them as clouds. And there are only two ways to do that. I've already taught this. For saturation to occur, the relative humidity was equal to 100% of 1. And we know that relative humidity is the ratio of the mixing ratio to the saturation mixing ratio. And that means that you can only increase the relative humidity to 100% by two ways: either by increasing the amount of water vapor in the parcel, you increase it, or second, by decreasing the saturation pressure, by decreasing the temperature. So you increase water vapor, you'll get saturation, or you cool the parcel, you cool the air. So there are only two ways through which you can make this relative humidity equal to 100%, and you can form cloud. So basically, these two are the ways. Okay. Now we'll just go. Is this clear? This thing. This thing is, you remember, is very important. It's a basic. Okay. If it is clear, then let us talk about different kind of fog which is there. So basically, there are three or four kind of fog. First is the most important one is the radiation fog. So as I've taken this from this lecture only. So what are radiation fog? So they are formed when the air near the surface cools down to its saturation temperature due to cooling by radiation at night. So what happens is that during night there is no sunlight. Okay, first thing, and Earth emits heat in the form of long wave radiation, because we have studied in the first class that Earth is, if we consider Earth as a black body at temperature 298 Kelvin or 288 Kelvin, so it emits radiation. With Stephen Boltzmann law, we can calculate that it emits radiation which peaks at the infrared radiation or long wavelength range. So what happens is that Earth emits heat into the space, and that leads to the cooling of the surface of Earth, because Earth is radiating away heat from its surface. Okay, so this is basically your long wave radiation. So the air which is near to the surface cools down to its dew point temperature or to its condensation temperature, and hence once it reaches a cools down sufficiently, then it reaches TD and it becomes saturated, and then clouds start forming. So this kind of fog which is formed near the surface is called radiation fog. Greater the long wave radiation, greater will be the radiation fog. So that is why in the if in the you must have seen that in the winter, if you can observe also, if the night is very clear, there are no clouds, then the long radiation emission is very large because there is no cloud in it. So a lot of long radiation gets emitted into space. So that's why the air which is near the surface cools down sufficiently, and we get a lot of fog. So in the northern plains, in the regions where we live, uh, in the winter season, if the night is very clear, then you can say that next morning it can be a very foggy morning. So you can make your traveling plans according to that. You can tell your friends that okay, it is very clear night, so there is a high chance that the next morning there will be a very dense fog. This is due to the radiation fog. The second kind of fog is the advection fog. Advection means transport of something by flow, transport of some substance by fluid flow, flow of fluid. That's the advection. So as given in this schematic, okay, another example of this radiation fog you must have seen is on the village over fields. Over field, what you must in the morning, if you go, you will see that over fields there is a very dense kind of fog is there just at the surface. That is because in the night there is a lot of radiative cooling, and hence the air near the surface cools down and fogs form. So that is you can observe in the area where there is not much building or we have open fields. The second kind of fog is the advection fog. Hello?
Yes, sir.
Yeah, any question?
No, sir, I was saying that I have observed that.
Yeah, that's why I was telling that you must have observed it. So that is basically radiation fog. Okay, now we'll talk about another kind of fog, which is called the advection fog. So how does advection forms? So the word advection means transport of substance by a fluid flow. So suppose there is some warm air which is present, and air has moisture in it, and it is flowing from land to some cold surface. This cold surface can be maybe lake, some cold water body, Okay, ponds, lake, anything which has lower temperature than land. So if the warm moist air travels over this colder surface, now due to this cold surface, the temperature of this warm air falls down, and if it falls down sufficiently to dew point temperature, fog starts forming. So that is when you see fog over some pond or lake, it is due to this advection. But it is just because of the fact that there is a warm moist air which is flowing over a colder surface, and hence fog forms. So this is another kind of fog. And then there is a fogs which are formed in the hilly region, which are called upslope and valley fogs. So there also, like is given the schematic. So upslope fog. Suppose there is some hill is there, and some moist air is flowing in this direction. Then due to this terrain, this warm moist air will start moving in upward direction, and as it will move in upward direction, it will cool down, and at a point its temperature will become equal to dew point temperature, and clouds will form. Similarly, suppose there is some valley fog in the, suppose this is shown in this figures, some valley. So what happens is that some in the hilly region temperature, the air is very cold, so that cold air flows along the terrain in the downward direction, and it reduces the air temperature which is there in the valley to a condensation point, and cloud starts forming here. So that is another way through which cloud of fogs form. These are actually clouds, kind of clouds which are called as fogs, valley fogs. So in plain region, we generally see these kind of fogs, radiation fogs and advection fogs. Okay, and we only see it in during winter season, because during winter season only the temperature is low, sufficiently low so that the it is cool to saturation or dew point. In summer season the temperature is very hot. Even the water bodies are very hot. So in that case, you don't get fog. So that is why you get fog only in winter season. Okay. So these were something related to fog. Now what I will do is that we will study a very important topic which is called the stability of the atmosphere. Or maybe vertical stability. Whenever we're talking about stability, it is the vertical stability in vertical direction. Just wait for 1 minute. So, what do you mean by the stability of this atmosphere, of vertical stability? So, when we are saying the stability of the atmosphere, what we are trying to understand is that suppose you have some air parcel at some position at some height, and you just displace it in upward direction. Just push it by some external forcing, by some external force. You just push it in one direction. Then will the air parcel will come down back to its original position, or will it keep going in the upward direction? If it keep going in the upward direction, it means it is in unstable equilibrium, because you just give a slight force, it will keep moving in the upward direction. In that case, the parcel will say it is in unstable equilibrium. And if it comes down, it is called stable. Stable because it is, you just push it upward, it will again come back down. So it is stable equilibrium. So basically, we are trying to understand this kind of stable and unstable equilibrium of an air parcel in atmosphere, and that is called as the studying the stability of the atmosphere. Okay, so there are certain assumptions again when we are trying to understand the stability of the atmosphere. So we know that we can understand the stability of the atmosphere by considering a air parcel, a part of the atmosphere which is air parcel. So I will go back to some class where I had written some assumptions. I won't write it again. So somewhere I wrote, yeah. So when I introduce the concept of air parcel, it is in which lecture? It is in, I think, week 4. No, not week 4. Week 5, okay. So in week 5, we just discuss about this air parcel. So there are certain assumptions. So when we are trying to understand the atmosphere, we are taking a small part of the atmosphere, which we call it as an air parcel, and there's certain property that this is a small control volume which satisfies the following conditions. 5. First is that it exists in the environment which is in hydrostatic equilibrium. That is, the parcel is situated in an environment which is surrounding the parcel. Environment means the area which is surrounding the parcel. That environment is in hydrostatic balance. That is, the vertical pressure gradient is balanced by the gravitational force. Okay. And we know that for a very, very large extent, for hundreds of thousands of kilometers of, if we take the area, then this hydrostatic balance is very accurate or very valid. The second assumption is that the parcel does not mix with surrounding. That is adiabatic process. It does not exchange any heat or mass with the surrounding. Del Q is 0. Third one is just the parcel movement does not disturb the movement. It's not very important. Then the fourth one is the related to second one only. The parcel rising and sinking motion should be adiabatic in nature. And then the last one is a very important assumption that at any given level, the parcel and the environment are at same pressure. What does it mean? It means suppose this is a parcel, and suppose the parcel's pressure is P dash and the environment pressure which is surrounding it is P. So at any level, parcel will quickly adjust its pressure to that of the environment. P dash is equal to P at any level. You take parcel down, the parcel pressure will become equal to the pressure which is there at this level. Suppose it is 800 hectopascal. So the P dash will become equal to 800. If you take the parcel at 750, so P dash will become equal to 750. So at any given level, the parcel and environment pressure are always same. So this is, you can remember, this is a very important assumption. So based on these assumptions, we'll just derive the vertical stability of the atmosphere. Okay. So suppose we have, let us assume that we have an air parcel with density rho dash and pressure P dash. Okay. And environment surrounding the parcel, environment surrounding the parcel has density rho and pressure P. Okay, so environment density is rho, environment pressure is P, parcel's density is rho dash, and parcel's pressure is P dash. So dash thing is related to parcel, and like is whenever there is a prime term, it is related to parcel, and whenever there is an unprime term, it is related to environment. Remember. Now, one of the assumptions which you know is that the environment surrounding the air particle is always in hydrostatic equilibrium. That is, del P by del Z is always equal to minus rho G, where rho is the density of the environment and P is the pressure of the environment. Okay, so this is equation 1. Second thing is that you can simply write the vertical equation of motion for the air parcel. Suppose you displace the parcel about its mean position, so it will have some vertical velocity acceleration. So we can simply write for parcel also this equation, del P upon del Z plus rho dash G is equal to minus rho dash Z double prime. Z double prime means d2z by dt square. So you have an atmosphere which is in an environment which is in hydrostatic equilibrium, and in that environment you have a small air parcel. You displace it in some direction such that it acquires some vertical acceleration, and that vertical acceleration will be a balance between the pressure gradient force and the gravitational force acting on that parcel. Okay, so these are the two equations of motion. Is it clear, this thing? This is for environment, and this is for uh, parcel. Now, remember one thing, the one assumption which we did, that at any level, parcel's pressure will be equal to the environment pressure. That means any time del P dash by del Z will be equal to del P upon del Z. This is an assumption of an air parcel, which is observed also. So if we just use this assumption in equation 1 and 2, we can write what we can write. We can write minus rho G is equal to minus rho dash G minus rho dash Z double prime. We can write this, right? This is equation 3. Or not equation 3, we'll just simplify it. So I've just put this, replace this with del P by del Z, and then equated 1 and 2, so this is the what we will get. Okay. Now, what we can write, we want to know what is the acceleration, vertical acceleration of the air parcel, that is Z double prime. So Z double prime will be equal to what? We can take G common. Rho will take Z this side and will bring rho G this side. So it will become G rho minus rho prime upon rho. So this is the vertical acceleration of the parcel, or this is also, you can call it as a buoyancy force. This is also called as a buoyancy force, which is acting against the gravity for the parcel. So now we'll do, because we want to derive the relation in terms of lapse rate, gamma. So for that we have to go from rho to gamma. So in order to do that, what we'll do is that we know that from ideal gas, P is equal to rho RT. Okay, so P upon rho is equal to RT. So rho has an inverse relation with temperature. Okay, so we can just write it as Z double prime is equal to G. Now, since this air which we have some water vapor also, so we instead of just giving temperature, we replace temperature with virtual temperature. Okay, because we know that virtual temperature is a temperature when is the temperature is a hypothetical temperature which we take into account when we are trying to study a parcel which has moisture. So it will be equal to what? TV prime minus TV upon TV. Simply this, rho is inversely proportional to T. Okay, so rho upon rho prime is equal to t prime upon t. Those things I have done. So this way, whenever there is row, I have replaced it with prime term, and whenever I have prime, I have replaced with unprime term. So we'll get this. Now we know that from the lab state that TV bar is equal to TV at the surface minus gamma V dz. This is lapse rate. Similarly, this is for parcel. Whenever you have prime term, this is for parcel. Similarly, for environment, TV is TV0 minus gamma V dz, where gamma V is the environment lapse rate and gamma V prime is the parcel lapse rate. Gamma V is the lapse rate of parcel and lapse rate for environment is gamma V prime. Okay. Now at surface, both TV naught at surface, both TV naught is equal to both parcel and the environment will have same virtual temperature. So you can just write it as, you can just remove the prime. So TV prime will also become TV naught minus gamma V prime dz. So these are two important equations. Now substitute this back into here. So your z double prime will be equal to g upon TV. Okay. TV prime is what? TV naught minus gamma V dash dz minus of TV. TV is what? TV naught minus minus will become plus. So plus gamma V dz. Okay. So this term will get cancelled out. So the vertical acceleration or the buoyant acceleration of the air parcel will be g upon TV and gamma V minus gamma V dash dz. So this is the acceleration of the air. Very important term. So this is the acceleration, vertical acceleration of air parcel in term of lapse rate of environment and parcel. The environment lapse rate is gamma V and the parcel lapse rate is gamma V prime. Okay, so basically what you can write over here is that I can just confirm whether it is right. Yeah, it is right only. So now before we move to the solution of this equation, let us name this equation as equation number A. You must be knowing from your mathematical physics course or that suppose you have a differential equation d2x by dt square plus omega square x is equal to 0. So the solution of this kind of, you just find the complementary function and the particular integral. I hope you must be knowing this. So when you solve this,
Yes, sir.
so you get the solution in the form of sines and cosines, right? Something like this. So basically your solution is kind of sine and cosine term, something like this. This is sine, similarly this is cosine. So these are oscillations about mean position. So whenever you have this kind of solution, sines and cosines, that means your the system is oscillating about some mean position x is equal to 0. Or this kind of solution is called stable solution because it is moving about some mean position up and down, sines and cosines. So this is stable solution. In simple words, when d2x by dt square is equal to minus negative, because minus omega square x. Omega square is always positive, so when it is negative, you will get stable solutions. This is one thing. Second thing, you remember that the opposite, when d2x by dt square minus omega square x is equal to 0, that is when your d2x by dt square is positive. It's positive. In that case, your solution is in the form of exponential. So it will be somewhere maybe x is equal to e to the power some omega t or minus omega t, something like that. Okay. So and these exponential functions, are unstable in nature, because this is suppose e to the power, this is t, this is e to the power t. So it is unstable, means if it keeps on increasing, doesn't decay it. Okay, it keeps on increasing. Okay, similarly, suppose your function is exponential e to the power minus t. So t is equal to infinity, it will become some infinite. Similarly, if you term some e to the power minus t, so at t is equal to 0, it will be some very close to 1, and then it will like a decaying term. So it will be something like this. Okay, something like this maybe. So these are the unstable solutions. Means it will keep on growing. If you have this kind of solution, it will either exponentially start increasing, or it will decay exponentially. So these are unstable equation. So whenever you have you remember these two things. Now we'll apply these two things in this equation, because this is also double derivative of z with respect to t, similar to this. So now we'll have two cases. The first case is, we know z double dot is equal to, or we can also, yeah, z double dot is equal to g time up g upon tv gamma v minus gamma v prime. Okay, now times dz. Now just compare it with this equation. Now if this is negative, this z double dot or x double it is negative, this can only be negative if gamma v is less than gamma v prime. Correct? If gamma v is less than gamma v prime, this term will be negative, and hence your z double dot will be negative. And when z double dot is negative, you have stable solutions. Similarly, in second case, if gamma v, that is in environment lapse rate, is greater than the parcels lapse rate, in that case, your z double dot, since gamma v is greater than gamma v prime, so z double dot will be, this term will be positive. So z double dot will be positive, and that means you will have exponential kind of solution which is unstable. So this is unstable. Okay. So if we combine, and if third case is just if the environment lapse rate is equal to gamma v prime, in that case your z prime will become equal to 0. That is, the parcel will have no acceleration in the vertical direction. So in combining these three equation condition, we have three cases. If I will write like this. Okay. So case 1, when gamma v is greater than gamma v dash, it is when gamma v is greater than gamma v dash, it is called unstable equilibrium. Second is gamma v is less than gamma v dash. It is called stable. And for 0, if they are both equal to each other, then we call it as neutral. So you should remember this. So this we have just derived based on mathematics, based on this differential equation. Now there is a very easy way to remember this thing physically. So what is that? So you may ask me that okay, mathematically we are getting that when gamma v is less than gamma v dash, then z double dot is negative. We will get sinusoidal solution which is stable. But how? What does it mean in atmosphere? How to relate it? So simple. One very important thing is that in order to have unstable equilibrium means what? As I told, if you have some parcel and you displace it in vertical direction, it will keep on moving in the vertical direction. So that is your unstable equilibrium. Okay. So we know that this kind of equilibrium occur only if the parcel, this air parcel, will keep on moving upward only if it is warmer than its surroundings. The temperature of the parcel, if it is greater than the temperature of the surrounding, then it will be lighter because it is more warmer, so density will reduce, so it will keep rising. Okay, so and this will happen only when the lapse rate of parcel is less than the lapse rate of environment. That is, this is unstable case. Okay, so unstable case means gamma v gamma v is greater than gamma v dash. This is unstable. This is first case. This case. This case. Why? Simple terms. See, gamma v. If I just with the help of diagram, suppose this is the gamma v, lapse rate of environment, and this is the lapse rate of parcel, gamma v dash. The slope of this line is greater. That means it is. This is your temperature. This is your z. Okay. So at a given point, if both of them starts at a given point, since the lapse rate of environment is more, so the environment will be colder. Since the lapse rate of environment is more, at a given point, the temperature of the environment will be colder. And at that point, since the lapse rate of the parcel is less, it will be hotter than or warmer than its environment. And since the parcel is warmer than its environment, it will keep rising. So, second case about stable equilibrium. For stable equilibrium, we saw that gamma v dash, that is the lapse rate of environment parcel, should be greater than gamma v dash is greater than gamma v. This is for a stable case. I'll just draw this plot. This is temperature, this is height. So in this case, your parcel lapse rate is higher, that is gamma v dash, and the environment lapse rate is less. So at suppose this point, if you're trying to understand at any point, or maybe this point, you can say at this point, at this height z1, since the parcel's lapse rate is higher, it will cool down. It will be colder than its, because this is the temperature, right? This is temperature T dash of parcel, and this will be the temperature of environment, and this temperature is increasing in this direction. So at this point, since the lapse rate of parcel is greater than the lapse rate of environment, it will be colder than its environment, and since it is colder, it won't be self-buoyant, it won't rise, and it will come back to its original position. So this is the basic concept. So basic concept is that the parcel should be warmer than its surrounding or what we call as environment. So the parcel should be warmer than its surrounding environment at a given level so that it has so that it is in unstable equilibrium. So for unstable equilibrium, the parcel should be warmer. And the parcel can only be warmer if its lapse rate is less than the lapse rate of environment. The rate at which temperature of the parcel decreases is less than the rate at which environment lapse rate decreases. Okay, so this is the double quote I'm writing. So this is very important. So just by at any level, you just compare the temperature of parcel and the temperature of environment. If the parcel is at higher temperature than its environment, that then it means that it will keep on rising. It will keep on, this case, unstable equilibrium. Its temperature is higher than its environment, it means it will keep on rising. And the second case, if the parcel is colder than its environment, that it means it will be stable equilibrium. Why it is colder? It is colder because its lapse rate is greater than the lapse rate of environment. The rate at which the parcel cool down, that lapse rate is greater than the lapse rate of the environment. That's why it is. So these are the two cases. Okay, stable and unstable equilibrium. So both mathematically and using this equation as well as using your physical insight of lapse rate, you can just find out that why it is stable and unstable. Now, if we take equation A, if we take equation A, which is z double prime is equal to g upon dv gamma v minus gamma v prime dz. So this z double prime is equal to g upon dv gamma v minus gamma v prime dz, or you can just write it as minus g by dv gamma v prime minus gamma v dz, and we just compare with the simple this term. This is the equation of the simple harmonic oscillator, those kind of things, where omega is a frequency. So you can just write this as z double prime is equal to minus of n square dz, where n square is equal to g upon tv gamma v prime minus gamma v, or your n will be equal to under root of g upon tv gamma v prime minus gamma v. This is called the Brunt-Weissela frequency. Okay. This is a Brunt-Weissela frequency. So it is the frequency with which the air parcel will oscillate about its mean position if it is displaced, because this is under root value. Okay, so in this case gamma v dash should be greater than gamma v to get a valid value of n, right? So a real value of n. If it is negative, we'll get imaginary value. So, and we know that gamma v dash is greater than gamma v corresponds to which case? It corresponds to stable equilibrium case. Okay, so It is the frequency with which the air parcel will oscillate about its mean position, or it will do about the stable equilibrium, it will oscillate. And it is called the Brunt-Weissela frequency. Okay, so this is a very important topic. So very important numerical can come through this problem. Okay, so suppose I will just solve one simple numerical that calculate the Brunt-Weissela frequency or n of an air parcel whose not potential, its virtual temperature TV is, suppose it is given the question 280 Kelvin. It is lying at some pressure level at 750 hectopascal. The air parcel is situated at this level, and assume that the environment lapse rate gamma V is 6 Kelvin per kilometer, and the parcel lapse rate is, like parcel gamma P is 9.8 Kelvin per kilometer. So what will the Brunt-Weissela frequency? So using this formula, you can calculate n is equal to under root 9.81 meter per second square, which is G, 280 Kelvin given in the question. Gamma V dash means the parcels. So this is gamma V dash only. So it is 9.8 minus 6, which is environment lapse rate. Kelvin per kilometer, we'll convert kilometer into meter, so it will be 1000 meter. So it will be 9 point, meter will cancel, Kelvin cancel. So 9.81 divided by 280 times 3.8 divided by 1000. So when you calculate this, it will come out to be 0.0115 second inverse. So this is the frequency of oscillation of air parcel. Now before this, one question can be asked to you: will it oscillate or not? Will the air parcel oscillate or not? So for oscillation, you know this is condition. For oscillation, you need to have stable equilibrium. That is, your gamma V prime should be greater than equal to gamma V. And gamma V prime is here what? 9.8, which is greater than, gamma P is greater than gamma V. That means yes, the air parcel will oscillate about it because it will have stable equilibrium. So it will oscillate about its mean position. And the frequency is 0.115 second inverse. And the time period of oscillation is we know it's 2 pi by frequency. Frequency is n. So it will come out to be 544 second, or divide by 60, it will come out to be 9.07 minute. So that means if you have some air parcel at 750 hectopascal level, virtual temperature is 280 Kelvin, you displace this air parcel about its mean position, it will keep oscillating about this mean level with frequency of this, and time period of the frequency will be 9.07 minute. Okay, so one complete oscillation it will take around 9.9 minutes. So is this clear, the numerical?
Yes, sir.
Okay. Yeah, so this is the rough order of, in our atmospheric any process which we have, general processes. So the rough time period is close to this 9 minutes, 6 minutes, 10 minutes, or those things. So they are in the order of minutes. Okay. Now before there is another. This is one way of writing the Brunt-Weissela frequency. There is another way of writing the Brunt-Weissela frequency. Second form, Brunt-Weissela frequency in terms of potential temperature. Theta, because potential temperature is a conserved quantity in adiabatic process. So simple, it can be derived. So we know that potential temperature is what? Theta is equal to T into P naught upon P to the power chi, which is R by Cp. Since here we have moisture in it, so we'll replace everything with virtual temperature. TV, okay. Now we just take log both sides, so it will become log of theta V is equal to log of TV plus R by Cp log of P naught minus R by Cp log of P. You differentiate both sides, you will get del theta V by theta V is equal to del TV upon TV. This is a constant term, P naught, which is P naught is always for potential temperature, we take it to the 1000 hectopascal. So differentiating the constant will go down, so it will be zeros minus R by Cp grad del of P by P. Okay. Now divide all the sides by divide by del Z, both sides. What you'll get is sorry, this is we're dividing by del Z, so it will be okay. Now this is what del TV by del Z is what? It's lapse rate of the environment. Okay, so it will be gamma V. It is the lapse rate, the rate at which the environment temperature is changing with height. So it will be gamma V upon TV, and this will become P can we can write as rho R TV, and dP by dz we can write as minus of rho G. So R will cancel, rho will cancel. So we'll get what? Gamma V upon TV, minus minus will cancel. So it will be get plus G upon Cp TV. Now G upon Cp is the lapse rate. Gamma D we know. G upon Cp is gamma D. So sorry, this will be one mistake, that this del T V by del Z is minus gamma V, because we know when we derive dt by dz it comes out to be minus. There is a minus sign always, so in order to take care of that minus sign we just take it here, so it will be minus. And so we can take 1 by TV common, so what we'll get is gamma D minus gamma V. So this is what we are getting. Now this is the gamma V is the lapse rate of environment. Lapse rate of environment. And gamma D is the lapse rate of parcel, depending upon lapse rate of parcel, which is unsaturated. Which is unsaturated. Okay, so this is the lapse rate of the environment. This is the lapse rate of parcel. So we can, it is basically a gamma V dash only, gamma D. So we can just use this equation back into this. This equation, we can just replace gamma V minus gamma V prime. So what we'll get is that, maybe here, from here we can write. So when we'll replace gamma V prime minus gamma V upon TV, gamma V prime minus gamma V prime minus gamma V upon TV, we can replace, we can write it as d theta by 1 by this quantity. We can write it as we can replace it with this. Okay, so initially what it will become is that your n square which was g upon TV gamma V dash upon gamma V. This is what your n square was. In the terms of potential temperature, you can just replace it as and write it as, you can replace gamma V prime minus gamma by TV with this term. So your n square will become under root g upon theta V del theta V upon del z. This is another form of,
So n square or n?
oh sorry, this is n. Yeah, this was, I've taken under root, so thank you. Correct. So this is a Brunt-Weisel frequency in terms of potential temperature. Okay. So we know in order to have stable oscillations, for stable oscillation, you will have some frequency n, which is real. In order to have real frequency, this term will always need to be positive. So the potential temperature should increase with height. So for stable oscillations, for unstable, your n can be imaginary. There is, because there will be no oscillation. So we can just say that it is imaginary. And in that case, your del theta V upon del Z will be less than 0. So it will be a negative term in the under root. So it will be imaginary frequency. So it will be not oscillating. So this is another way through which you can represent the Brunt-Weisel frequency. So this is another, like they can ask you some question. For example, one question based on this formula is, if the potential temperature of environment, that is theta V, is increasing at rate of 3 Kelvin per 100 meters. So this is basically what? This is basically your del theta V upon del Z. The rate at which your potential temperature is increasing with height is given as 3 Kelvin per 100 meter. Okay. And the potential temperature of environment, that is the potential temperature of environment, that theta V is given to be 20 degrees centigrade. What will be the Brunt frequency of oscillation what will be the frequency of oscillation of the parcel in the environment? So its solution, straightforward. Del theta y by del z is given as 3 Kelvin per 100 meter. So in kilometers, what will it become? Or sorry, per 100 meter, it says 0.03 Kelvin per meter. Your theta v is given to be 293 Kelvin. So your n square will be g upon theta v del theta y by del z. So it will be 9.81 meter per second square divided by 293 Kelvin, and this is 0.03 Kelvin per meter. Kelvin, Kelvin cancel, meter, meter cancel. So your n square will come 0.001 if you solve it, 0 second square, or your Brunt Weisler frequency will be what? 0.031 second inverse. And the corresponding time period of oscillation will be 2 pi by n. It will come out to be 198 second or 3.30 minutes. So if you have an air parcel whose potential temperature is increasing at this rate, and initial potential temperature and the potential temperature of the not air parcel, but if you have the potential temperature of the environment is increasing at this rate, and the potential temperature of the environment at any level is given as 20 degrees centigrade, then this will be the frequency of the oscillation of the air parcel. So the frequency of the oscillation of the air parcel completely depends upon the temperature profile of the environment, theta v, and the rate at which it is changing. If we know the potential temperature at the environment and the rate at which it is changing, you can just find out the frequency of the oscillation of the air parcel in that environment. Yeah, so this is it. Now, is it too much for today, or there is one more topic, one short topic only? Shall I teach that?
Sure, sir.
Okay. Okay. So now comes the last topic based on this thing. It's called your what's this? There's something called conditionally stable or unstable. Conditionally stable or unstable atmosphere. Okay. So till now you must have understood that in order to find out the stability, there is this condition: gamma v prime is greater than equal to gamma v. So if the lapse rate of parcel is greater than lapse rate of environment, that means at a particular level your parcel will be colder since its lapse rate is greater. and hence it will be stable. Similarly, if the lapse rate of parcel is less than the lapse rate of environment, that means at a given point, the parcel will be hotter than environment. This is with respect to environment. With respect to environment. So since it is parcel is hotter, that means it will be self-buoyant and it will be unstable. It will keep rising. If you just push it in the upward direction, it will keep rising. And if both are equal, that means there will be no oscillation. Z double dot will be equal to 0. No vertical acceleration. Okay. Now, suppose we just summarize all the things in single figure. Suppose this is your temperature axis increasing in this direction. Similarly, you have this in vertical direction. There is your height is increasing or pressure level is in the vertical direction. Okay. Now we know that gamma d, the parcel can have this gamma v. First of all, you know one thing, gamma v is always given, but gamma v dash can be gamma d if parcel is unsaturated, because this prime means the lapse rate of parcel. The parcel can be unsaturated, that is gamma d, and if it is saturated, that is gamma w. So if the air parcel is saturated, its lapse rate will be gamma w, which is also called as saturated adiabatic lapse rate, SALR. And if the parcel is unsaturated, then it will follow the dry adiabatic lapse rate, DALR. Okay. So these two things you know. Now, we know that gamma D value is, we know the value of DALR is what? It is around, this is that line, gamma D, which is 9.8 Kelvin per kilometer. We also know the value of the saturated adiabatic lapse rate. It is less. It is somewhere, maybe you can assume it to be 4 Kelvin, 4 Kelvin per kilometer. This is gamma W. Okay. So these two, so your actually lapse rate is increasing in this direction. If it is lying on this, means it is 0. If it is going in the positive direction, gamma W is 4 Kelvin per kilometer, gamma D is 9.8 Kelvin per kilometer. Okay. Now, suppose this is the case for the parcel. The parcel can have either gamma D lapse rate or it can have gamma W. Now, environment, suppose your environment has lapse rate which is lying over here. In that way, your gamma V is greater than gamma D and is also greater than gamma W because it is very high. Gamma V is lying. So in this part of the atmosphere, it is case 1. For case 1, when gamma V is greater than gamma D and gamma W, that means gamma V is greater than gamma V prime, because these are the lapse rate of the parcel, so gamma V prime. Now this case is what? Gamma V is greater than gamma V prime is what? Gamma V greater than gamma V prime means this is case 1.
Unstable.
Always unstable, right?
Yes, sir.
So so this is the case for always unstable. So if the environment lapse rate is greater than 9.8 Kelvin per kilometer, that means that parcel in that environment will always be unstable. If you displace it, it will always keep on moving in one direction. If it will rise it will keep rising. If you sink, it will keep sinking. So that is always unstable. This is case 1. Maybe I will highlight it with different color. This is case 1, like in this direction. Similarly, we can have case 2. What is happening in case 2 is, in case 2, suppose your environment lab set is somewhere here, gamma V. And that means gamma V is less than gamma W, and also it is less than gamma D. That is, your environment lapse rate is always less than your partial lapse rate. So at a given point, it will always be case of stable equilibrium. So always stable. So if your parcel is an environment whose lapse rate is greater than 4 Kelvin per smaller than 4 Kelvin per kilometer, in that case your environment will always be stable no matter what. So these are two extreme cases. Now in between these two cases, if the parcel is if the environment lapse rate is lying somewhere in these between these two regions, gamma D and gamma W, somewhere here. Now, now it can gamma V can be, now in third case, this is called the case third. In case third, your gamma V is greater than gamma D. Okay. Oh, sorry, gamma V is greater than gamma W. Gamma V is greater than gamma W, and gamma V is less than gamma D. Gamma V is less than gamma D. So this case means if the parcel is saturated, then it will follow this case, gamma W. Its lapse rate will be gamma W. And that means gamma V is greater than gamma V prime. That is unstable. Then the parcel will be unstable. Or second case, if the parcel is unsaturated, this is the parcel is unsaturated, it will follow dry adiabatic lapse rate. And in that case, its lapse rate gamma V dash is greater than 5, so it will follow this table. So the thing is that if the environment lapse rate, is greater than gamma W and less than gamma D, then the parcel will be stable if it is unsaturated. Parcel will be stable if it is unsaturated, because if it will be unsaturated, it lapse rate will be gamma D, and then it will satisfy this condition. And parcel will be unstable if it is saturated, because if the parcel will be saturated, that means it will follow gamma W, and in that case we know that gamma V is greater than gamma W, and gamma V greater than gamma W means unstable in this case. So that is called, this is called conditionally stable or unstable. This region is called conditionally stable or unstable region. So depending upon the saturation or the unsaturation of the parcel, whatever case it is, the parcel can be stable or unstable. So basically there are three regions. Case 1, the parcel will always be unstable. Case 2, parcel will always be, whether it is saturated, unsaturated, anything, it will always be stable. And in middle case, it depends whether it is saturated or unsaturated. If it is saturated, then it is unstable. If it is unsaturated, then it is stable. So this is the basic fund of conditionally unstable or stable atmosphere, middle section. So there are only three cases which can occur in an atmosphere. These are those three cases. So this was the last topic for today. And assignment, I think it's straightforward only. So I will just quickly go through them. So which of the following cause acid rain? So all these are the sulfur dioxide, nitrogen dioxide, and all these things are cause acid rain. So and the size of the drizzle, this thing I have will cover in the next class, precipitation and all. So it is 0.5 meter. Okay. Okay. Now the supersaturation corresponding to relative humidity of 100.6%. So we know that F is equal to 100%. The parcel is said to be saturated, and if you further increase its, if you further cool down the parcel, it will become supersaturated. If F becomes greater than 100%, then we call the parcel to be supersaturated. So generally, its humidity is 100.6. So 100.6 minus 100. So it is supersaturated by 0.6%. Okay. This you must be knowing. For hydrostatic equilibrium, pressure gradient force is balanced by the gravity. So easy. Fifth one, which of the following type of clouds is found at the highest altitude? So basically this is something called noctilucent clouds, which are only found at very, very height, 60 kilometers or greater than that. So it is above troposphere. It is in mesosphere they are found, and they're only located at poles region, like 60 to 90 degree north or 60 degrees south to 90 degrees south. So close to poles only we can observe them. So those are noctilucent clouds. The cooling of air near the Earth's surface due to long wave radiation, we already studied today, it's called radiation fog. The conditionally stable atmosphere, okay. So the conditionally stable atmosphere, for that, what could be the condition? So I think this is the answer for it. For the conditionally stable atmosphere means we're talking about this region, case 3. And for that, your dry adiabatic lapse rate, your environment lapse rate, that is ELR, that is environment lapse rate, should lie between the dry adiabatic lapse rate and the saturation adiabatic lapse rate. SALR is less than ELR. So case first option is the right option for that. Okay. The Brunt-Weissela frequency represents the stable atmospheric oscillations. So oscillation with which the air parcel will do the stable oscillations about its mean position. Ninth question, if an environment lapse rate is faster in comparison to the parcel lapse rate, a parcel displaced from the mean position will what? If environment lapse rate is gamma v is greater than gamma v prime, that means that at particular level, environment will be colder and parcel will be warmer. So parcel will keep rising. So if you parcel displaced from mean position will keep rising. Okay, gamma v is greater than gamma prime. So it is unstable case. So if a parcel is displaced, it will keep rising because it is warmer than its environment. Then which of the following cloud will not produce any reasonable amount of precipitation? Nimbo means it will produce. These are middle level clouds. Alto means middle level clouds. They will also have some precipitation. Cirro is high level clouds. The precipitation, they do not lead to precipitation on surface. So cirrostratus is the answer. The value of saturated lapse rate will decrease in the ambient temperature. So that is basically coming from the value of saturated adiabatic lapse rate will decrease with decrease in ambient temperature. So we have the formula for the saturated adiabatic lapse rate. So from that you can calculate. So I think from here they are trying to understand. So this has a T term from here. So from there you can just say that if what will be change in the temperature, what will be the effect of temperature on the lapse rate. So omega is what? Omega is epsilon by P ES. So omega is directly proportional to exponential to the power minus b by t. So if t will decrease, this will increase. So omegas will decrease, and hence your lapse rate will maybe decrease. So you can just by that formula you can just find the answer. It will decrease. Now, which of the following thermodynamic quantity remains a constant? So as soon as you see this, just go with the potential temperature. Potential temperature remains constant during the adiabatic process. Okay. Yeah. So that's it. So whatever I taught today, I'm not expecting that you understand 100% as of now, but you can go through the notes once or twice, and you don't get it, you can ask me in the next class or whenever you want. Okay.
Okay, sir.
Okay. So in the next class, we'll meet next Sunday. We'll study about precipitation. Okay then.
Okay. Thank you, sir.
Thank you. Bye.